Baltimore, 1946. Western Electric's massive cable factory hums with the precision of American industrial might. Molten lead flows at 650 degrees through chambers, where telephone cables receive their final protective coating. Senior engineer Carol Tullos watches his team create infrastructure built to last generations, cables that will carry America's conversations for decades to come. Corporate executives and public health officials demand the same thing. Abandon lead forever. Switch to cheaper aluminum, use modern plastics, cut costs by 75%. European engineers visiting the Baltimore plant declare the lead process impossibly complex and unnecessarily expensive. The entire telecommunications industry agrees. Good enough is good enough. But in 2024, a routine fiber optic installation in Baltimore reveals something that shatters every assumption about modern engineering. Technician Maria Santos tests a 1948 Western Electric cable still buried underground after 76 years of continuous service. Her digital analyzer shows readings that seem impossible. Signal clarity better than today's fiber optic systems. Zero corrosion. Perfect voice transmission after 3/4 of a century. Meanwhile, fiber cables installed just 9 years earlier are failing at 30% rates. The advanced materials that were supposed to last 25 years need replacement every decade. The secret that American engineers perfected in 1946, then lost forever. J. Carol Tullos arrived at Western Electric's Baltimore works before dawn on December 3, 1946, his breath visible in the frigid air as he walked past the sprawling complex that had replaced Riverview Amusement Park, where families once rode carousels and Ferris wheels. 2.5 million square feet of precision manufacturing now housed the largest cable production operation in America. 6,200 workers would clock in within the hour, ready to build the backbone of the nation's telephone network with tolerances measured in thousandths of an inch. The engineering problem that awaited Tullos in his cramped office defied every solution Bell Labs had proposed over the past 18 months. Lead-sheathed telephone cables had carried America's conversation since 1888, with flawless performance. The heavy metal coating stopped every molecule of moisture from penetrating paper insulation, preserved copper conductors indefinitely, and delivered crystal-clear voice transmission across thousands of miles. But lead was poisonous, and the War Department wanted it eliminated from all civilian infrastructure. Public health officials had issued ultimatums. AT&T executives saw dollar signs in the potential savings. Lead cost 3 times more than aluminum alternatives, and nearly 4 times more than experimental plastic compounds. Tullos spread the latest test, results across his desk as steam hissed through the building's radiators. 27 different plastic formulations had been subjected to accelerated aging tests over the past 6 months. Every single sample showed moisture infiltration rates that would compromise signal quality within a decade. Aluminum sheathing performed better, but suffered from galvanic corrosion when in contact with copper conductors, creating electrical resistance that degraded voice transmission over long distances. The corporate executives dismissed these concerns as theoretical problems that field engineers could solve with periodic maintenance. The human stakes became clear during a staff meeting later that morning when William Bradford, AT&T's senior executive for operational efficiency, presented his analysis to the assembled engineers. Bradford's Harvard MBA credentials carried weight in corporate boardrooms, but his spreadsheets revealed a fundamental misunderstanding of telecommunications infrastructure. He calculated return on investment based on 5-year projections, treating telephone cables like consumer appliances that would be replaced regularly rather than permanent installations expected to function for generations. "Gentlemen," Bradford announced, adjusting his wire-rimmed glasses as he pointed to projected cost savings, "our competitors are achieving 75% material cost reductions by switching to modern alternatives. Good enough engineering at acceptable prices will capture market share that perfectionist approaches cannot justify." The executives nodded approvingly at the financial projections, but Tullos noticed the manufacturing supervisors exchanging skeptical glances. Frank Kowalski, the Polish immigrant's son who supervised lead extrusion operations, raised a calloused hand from the back of the room. "Mr. Bradford, with respect, a cable installed today should carry calls when my grandson starts working. These plastic samples we've been testing, they're failing after 18 months in simulated underground conditions. That's not theoretical. That's mathematical certainty of network collapse. Bradford dismissed Kowalski's concerns with corporate confidence that prioritized quarterly earnings over engineering reality. Frank, modern materials science has advanced considerably. Laboratory projections indicate these alternatives will provide adequate service life at substantially reduced costs. We cannot allow perfectionist engineering to price us out of competitive markets. Dr. Harold Simpson from Bell Labs supported Bradford's position with scientific authority that carried weight among the assembled engineers. His materials science credentials were impeccable, and his laboratory data supported the corporate push toward cheaper alternatives. Our accelerated aging tests show acceptable performance degradation curves, Simpson explained, displaying charts that compress decades of real-world conditions into months of controlled laboratory exposure. Aluminum sheathing with proper corrosion inhibitors should provide 20 to 25 years of reliable service. Plastic compounds show similar longevity with appropriate stabilizing additives. Tulloss studied Simpson's data with growing concern. The Bell Labs tests used controlled temperature and humidity conditions that bore little resemblance to the harsh environments where cables would spend decades buried underground. Real-world installations face temperature swings from below freezing to over 100 degrees Fahrenheit, groundwater with varying mineral content, and mechanical stress from settling soil that laboratory simulations couldn't replicate accurately. The impossible choice crystallized over the following weeks as federal regulations arrived with non-negotiable deadlines. Public health officials would not permit lead cable manufacturing beyond December 31st, 1948. Corporate accountants saw only immediate cost savings from material substitutions. Wall Street analysts demanded explanations for Western Electric's excessive manufacturing expenses compared to competitors who had already switched to cheaper alternatives. Tulloss realized his engineering team had perhaps 2 years to perfect lead cable manufacturing before the process would be banned forever. They weren't simply building telephone infrastructure, they were preserving a lost art of American manufacturing excellence before corporate cost-cutting destroyed the institutional knowledge forever. Every cable produced during this final period would need to carry conversations for decades after the engineers who designed them had retired. The weight of this responsibility became evident during quality control testing in late December. Prototype plastic sheathed cables showed promising initial performance, but moisture testing revealed catastrophic weaknesses that validated every engineering concern. After 6 months of simulated underground conditions, signal quality dropped 40% as water molecules penetrated the polymer matrix and degraded paper insulation. Laboratory accelerated, aging confirmed the worst fears. Plastic sheathed cables would require complete replacement every 10 to 15 years, forcing network rebuilds every generation rather than creating permanent infrastructure. Manufacturing floor supervisor Kowalski understood what the corporate executives refused to acknowledge. Standing beside the lead extrusion equipment that operated at temperatures approaching 700 degrees Fahrenheit, he trained workers to handle molten metal with precision that rivaled surgical procedures. Each cable required 47 individual quality checks, testing conductivity, moisture resistance, and mechanical strength. The process was complex, expensive, and unforgiving, but it produced infrastructure built to outlast the companies that created it. The doubt crept in as 1947 began, with increased corporate pressure to accelerate the transition to cheaper alternatives. Tulloss's team had perfected controlled atmosphere lead extrusion that removed 99.97% of air pockets causing moisture infiltration, but executives viewed this precision as unnecessary perfectionism that increased manufacturing costs without improving short-term profitability. The engineering excellence that would preserve American telecommunications infrastructure for generations was being sacrificed for quarterly earnings reports that would be forgotten within months. The breakthrough came on February 14, 1947, when Tulloss's engineering team achieved what Bell Labs had declared impossible to mass produce. Instead of simply coating cables with molten lead using traditional methods, they created a sealed chamber system where lead alloy flowed around paper-insulated copper conductors under precisely controlled atmospheric conditions. The innovation wasn't in the materials. 99% lead with 1% antimony for tensile strength remained the same formula used since the 1890s. The revolution was in American precision manufacturing that turned art into science. Frank Kowalski supervised the construction of the controlled atmosphere extrusion chamber with obsessive attention to detail that reflected his immigrant family's pride in American craftsmanship. The chamber maintained internal pressure at 3,200 pounds per square inch, while lead alloy flowed at exactly 650 degrees Fahrenheit. Temperature variations of more than 2 degrees would create microscopic air pockets that could admit moisture over decades of service. Kowalski trained his 180-person crew to monitor dozens of variables simultaneously, transforming skilled workers into precision operators who understood that thousandth of an inch tolerances determined whether cables would last 15 years or 75. The paper insulation received petroleum-based treatment compounds that prevented bacterial degradation through chemical stabilization rather than toxic preservation. Each copper conductor pair was wrapped with paper treated to resist moisture absorption, electrical breakdown, and mechanical stress from thermal expansion cycles. The process required 47 individual quality control checkpoints, testing conductivity, dielectric strength, moisture resistance, tensile strength, and dimensional accuracy. Where European cable manufacturers relied on master craftsmen's intuitive feel for proper lead application, Western Electric measured everything with instruments calibrated to engineering tolerances that eliminated human error. German engineering delegations visiting Baltimore Works in March 1947 declared the American process impossibly complex after observing the systematic coordination required to maintain quality standards. Their traditional apprenticeship system produced skilled craftsmen who could judge lead temperature by color and flow rate by sound, but this intuitive knowledge couldn't be transferred quickly or measured objectively. Tulloss responded to their criticism with characteristic directness. Complex manufacturing creates simple service. We engineer difficulty into the factory so customers experience reliability in the field. The controlled atmosphere chamber removed 99.97% of air pockets that caused moisture infiltration over time. Oxygen and nitrogen molecules trapped during traditional lead coating processes created microscopic voids where water vapor could condense and eventually penetrate paper insulation. The American innovation used inert gas atmospheres and pressure differential techniques to eliminate these failure points through systematic engineering rather than hoping skilled craftsmen would achieve consistent results through experience and intuition. Quality control supervisor Margaret Chen, one of the few women engineers at Baltimore Works, documented performance data that revealed the dramatic improvement in cable reliability. Traditional lead coating methods produced cables with moisture resistance lasting 20 to 30 years in optimal conditions. The controlled atmosphere process created cables that showed zero measurable moisture penetration after accelerated aging equivalent to 50 years of underground service. Chen's meticulous testing protocols measured electrical characteristics with precision instruments that detected signal degradation invisible to human perception. The petroleum-based paper treatment represented another American innovation that European manufacturers had never considered necessary. British and German cable makers used untreated paper insulation, assuming lead sheathing would provide complete moisture protection indefinitely. American engineers recognized that even microscopic moisture infiltration would eventually reach paper insulation, requiring chemical stabilization to prevent degradation. The treatment process involved multiple chemical baths that saturated paper fibers with compounds preventing bacterial growth, oxidation, and mechanical breakdown from thermal stress cycles. Dr. Harold Simpson from Bell Labs initially dismissed the controlled atmosphere process as manufacturing overkill that increased production costs without proportional performance benefits. His laboratory simulations suggested traditional lead coating methods provided adequate moisture protection for the 20 to 25-year service life he considered reasonable for telecommunications infrastructure. Simpson's academic background emphasized theoretical materials, science over practical manufacturing experience, making him skeptical of field engineers' claims that real-world conditions differed significantly from controlled laboratory testing. The ultimate validation came during Bell Labs' comprehensive testing program conducted throughout the summer of 1947. 1,000 Western Electric cables manufactured using the controlled atmosphere process were buried in simulated worst-case conditions designed to replicate 50 years of underground service. The test environment included temperature cycling from -20 to +120 degrees Fahrenheit, exposure to acidic groundwater with high mineral content, mechanical stress from simulated soil settling, and electrical loading equivalent to maximum capacity operation. Results exceeded every engineering prediction. After 12 months of accelerated aging equivalent to 50 years of real-world service, the cables showed 0 failures, perfect voice transmission quality, and no measurable signal degradation. Moisture content remained undetectable even with instruments capable of measuring parts per million humidity levels. Electrical characteristics matched original specifications with precision that impressed even skeptical Bell Labs scientists who had expected some performance decline over the accelerated testing period. Frank Kowalski's manufacturing team achieved production rates that demonstrated American industrial efficiency without compromising quality standards. The Baltimore Works facility produced 9 miles of perfect lead cable daily by late 1947, with each cable containing 600 wire pairs capable of carrying 1,200 simultaneous telephone conversations with 0 crosstalk between circuits. Quality control reports documented that 99.8% of cables passed all acceptance tests, an industry record that European manufacturers using traditional methods could not approach. The worker training program reflected American systematic approaches to skill development that contrasted sharply with European guild traditions. Instead of relying on multi-year apprenticeships where knowledge transferred slowly through observation and practice, Western Electric created detailed procedures that enabled workers to achieve expert-level performance within months of training. Kowalski personally demonstrated every critical operation, ensuring that each team member understood not just what to do, but why specific tolerances mattered for long-term cable performance. Temperature control emerged as the most critical factor in achieving consistent results. The lead alloy had to flow at exactly 650 degrees Fahrenheit, hot enough to eliminate air pockets, but not so hot that it damaged paper insulation or created thermal stress in copper conductors. Kowalski's team used precision pyrometers to monitor temperature at 16 locations throughout the extrusion chamber, with automatic shutdown systems preventing operation outside acceptable ranges. This systematic approach eliminated the temperature variations that plagued traditional lead coating methods, where craftsmen judged heat levels by visual observation. The cooling process required equal precision to prevent thermal shock that could crack lead sheathing or create internal stress concentrations. Cables emerging from the extrusion chamber entered controlled cooling baths, maintained at exactly 40 degrees Fahrenheit, with conveyance speeds calculated to ensure gradual temperature reduction over precisely timed intervals. The entire process from molten lead application to final cooling took 18 minutes per cable section, compared to traditional methods that rush through cooling phases to maximize production speed at the expense of long-term reliability. October 21, 1947, marked the pinnacle of American cable manufacturing excellence when Baltimore Works achieved what industry experts had declared impossible: perfect production at industrial scale. The morning shift began at precisely 6:30, with Frank Kowalski inspecting every critical system before his 180-person crew took their positions. Steam gauges read normal pressure, lead furnaces maintained exactly 650 degrees Fahrenheit, and the controlled atmosphere chambers showed optimal nitrogen purity levels. By 7:15, molten lead flowed through precision extrusion dies at 18 inches per minute, while paper-insulated copper conductors received their protective coating with tolerances measured in thousandths of an inch. The mathematics of perfection became visible in the quality control data that Margaret Chen compiled throughout that historic day. 9 miles of telephone cable emerged from the Baltimore production lines, each containing 600 wire pairs capable of carrying 1,200 simultaneous conversations across thousands of miles without signal degradation. Every cable section underwent 47 individual tests measuring electrical conductivity, moisture resistance, tensile strength, dimensional accuracy, and dielectric performance. The rejection rate fell to 0.2%, an achievement that European manufacturers using traditional methods considered mathematically impossible. Kowalski moved through the manufacturing floor with the confidence of a master craftsman who had transformed industrial art into engineering science. His Polish immigrant background instilled respect for precision work, but his American training emphasized systematic approaches that eliminated reliance on individual skill alone. Workers at each station understood exactly how their operations affected cable performance decades into the future. The man operating lead temperature controls knew that 2-degree variations would create microscopic air pockets, causing moisture infiltration in 20 years. The woman monitoring pressure differentials recognized that inconsistent chamber atmosphere would compromise paper insulation integrity over generational service periods. The lead extrusion process represented the culmination of American manufacturing innovation applied to traditional materials. Where European craftsmen relied on visual assessment of molten metal flow, Western Electric used precision instruments measuring temperature at 16 locations, pressure at 12 monitoring points, and flow rates calculated to eliminate air entrapment. The lead alloy composition remained unchanged from 19th century formulations: 99% pure lead with 1% antimony for tensile strength, but the application methods achieved consistency that individual craftsmanship could never match systematically. Dr. Harold Simpson arrived from Bell Labs during the afternoon shift to observe production methods he had initially dismissed as unnecessarily complex. His materials science background emphasized theoretical performance rather than manufacturing practicalities, leading him to underestimate the precision required to achieve generational reliability in real-world installations. Watching Kowalski's team coordinate dozens of variables simultaneously while maintaining quality standards, Simpson began recognizing that American systematic approaches produced results superior to European traditional methods despite higher initial complexity. The cooling bath system demonstrated American engineering's attention to thermal management details that traditional manufacturers ignored. Cables emerging from lead extrusion entered precisely controlled 40-degree Fahrenheit baths with conveyance speeds calculated to prevent thermal shock while ensuring complete temperature stabilization. European methods rushed through cooling phases to maximize production rates, creating internal stresses that would manifest as premature failures after years of underground service. American engineers understood that 18 minutes of controlled cooling prevented decades of field problems. Quality control testing revealed performance characteristics that exceeded engineering specifications originally considered optimistic. Electrical resistance measurements showed conductivity values within 0.5% of theoretical maximums for pure copper conductors. Moisture penetration tests using accelerated aging techniques, equivalent to 50 years of underground service, detected zero water infiltration through lead sheathing, manufactured using controlled atmosphere methods. Signal transmission quality measurements indicated voice clarity superior to laboratory standards, with crosstalk between adjacent wire pairs eliminated through precision conductor spacing and electromagnetic shielding. The human element of manufacturing excellence became evident in conversations between experienced workers and newer employees throughout the production facility. Kowalski encouraged questions about why specific procedures mattered for long-term performance, rather than demanding blind adherence to written instructions. Workers learned that consistent lead temperature prevented crystalline structure variations that could create weak points decades later. They understood how atmospheric purity during extrusion eliminated oxidation that would eventually compromise conductor connections. This systematic knowledge transfer created manufacturing expertise that transcended individual craftsmen's intuitive skills. Production metrics for October 21st established records that would never be equaled in American telecommunications manufacturing. 9 miles of cable represented sufficient infrastructure to connect 4,500 residential telephone subscribers with trunk lines capable of handling peak calling volumes without congestion. At full capacity, these cables could simultaneously carry conversations equivalent to the entire population of a medium-sized city communicating with perfect voice quality across continental distances. The petroleum-based paper treatment process achieved chemical stabilization that prevented bacterial degradation under conditions that would destroy untreated cellulose insulation within months. Each copper conductor pair received paper wrapping saturated with compounds, preventing oxidation, moisture absorption, and mechanical breakdown from thermal expansion cycles. The treatment chemicals cost 4 times more than untreated paper, but field testing demonstrated that this investment would eliminate replacement requirements for generational service periods. Bell Labs, conducting independent verification testing throughout the day, documented results that challenged fundamental assumptions about telecommunications infrastructure economics. Traditional business models assumed cable replacement every 15 to 20 years as acceptable operational expenses. Western Electric's controlled atmosphere lead cables showed performance characteristics suggesting service lives extending beyond 50 years without measurable degradation. The initial manufacturing costs appeared excessive compared to cheaper alternatives, but life cycle analysis revealed dramatic long-term savings from avoided replacement expenses. William Bradford arrived from AT&T corporate headquarters during the evening shift to observe production methods that his financial projections had dismissed as economically unjustifiable. His Harvard MBA training emphasized cost minimization through material substitutions and process simplifications that would reduce immediate manufacturing expenses. Watching the systematic coordination required to achieve perfect quality standards, Bradford began questioning whether his spreadsheet analyses adequately accounted for long-term infrastructure reliability costs. The final quality control report for October 21st documented achievement that represented the pinnacle of American industrial excellence applied to telecommunications infrastructure. 99.8% of cables passed all acceptance tests, with rejection causes attributed to equipment calibration variations rather than systematic manufacturing defects. Voice transmission. Quality measurements exceeded laboratory standards for signal clarity, frequency response, and crosstalk elimination. Moisture resistance testing showed 0 water penetration through lead sheathing after accelerated aging equivalent to decades of underground service. Frank Kowalski addressed his crew during the shift change ceremony that evening, acknowledging their role in creating telecommunications infrastructure that would carry America's conversations long after the workers who built it had retired. "We don't just make telephone cables," he told the assembled manufacturing team. "We build bridges between people that will last longer than the buildings we work in. Every cable that left here today will connect families, businesses, and communities for the next 50 years. That's the responsibility we carry, and that's the pride we earn." The storm gathering against Western Electric's lead cable manufacturing became undeniable on January 15, 1948, when William Bradford presented his final cost analysis to the AT&T Board of Directors. His presentation reduced 50 years of telecommunications infrastructure to quarterly profit projections that made lead cables appear economically indefensible. Switching to aluminum sheathing would cut material costs by 60%, while plastic alternatives promised 75% savings. Wall Street analysts attending the meeting demanded immediate explanations for Western Electric's excessive manufacturing expenses that inflated production costs compared to competitors who had already adopted cheaper materials. Bradford's Harvard MBA credentials carried authority in corporate boardrooms where engineering expertise was viewed as secondary to financial optimization. His spreadsheets demonstrated compelling short-term savings that would improve quarterly earnings reports and boost stock valuations. The presentation included no analysis of long-term infrastructure replacement costs or field reliability data from cables manufactured using controlled atmosphere lead extrusion. Bradford dismissed such considerations as theoretical concerns that future engineering teams could address through improved maintenance procedures and periodic equipment upgrades. The impossible choice crystallized when federal health regulations arrived with non-negotiable deadlines that eliminated any possibility of compromise or delay. Public health officials, citing mounting evidence of lead toxicity in civilian infrastructure, mandated complete cessation of lead cable manufacturing by December 31, 1948. The regulation included no exceptions for superior performance characteristics or long-term reliability advantages. Lead was poisonous, period. Alternative materials would be required regardless of engineering consequences or economic implications over generational service periods. J. Carroll Tulloss reviewed the regulatory documents with growing recognition that his engineering team faced an insurmountable deadline. 18 months remained to perfect processes that had required 3 years to develop initially. The controlled atmosphere lead extrusion system represented accumulated knowledge from hundreds of manufacturing trials, thousands of quality control tests, and systematic refinement of tolerances measured in thousandths of an inch. Transferring this expertise to alternative materials would require starting from zero, while corporate executives demanded immediate cost reductions and accelerated production schedules. Corporate pressure intensified throughout the spring of 1948 as competitors gained market share by offering telecommunications cables at prices Western Electric could not match while maintaining quality standards. Companies using aluminum sheathing underbid Western Electric contracts by 40%. Manufacturers adopting plastic alternatives offered even greater savings while promising adequate performance for projected service requirements. AT&T executives faced shareholder demands for explanations about why Western Electric's superior engineering justified premium prices that customers increasingly refused to pay. The catastrophic validation of every engineering warning came in June 1948, when a prototype plastic sheathed cable installed 18 months earlier failed spectacularly during routine maintenance inspection. The cable had been buried in Baltimore's Harbor District, where underground conditions included high humidity, temperature variations from freezing to over 100 degrees Fahrenheit, and groundwater with elevated mineral content. Field technicians discovered 40% signal degradation caused by moisture infiltration that had turned paper insulation into useless pulp, while copper conductors showed extensive corrosion from electrochemical reactions with contaminated groundwater. Frank Kowalski accompanied the field inspection team to document failure mechanisms that his manufacturing experience had predicted would occur under real-world conditions. The plastic sheathing showed microscopic cracks invisible to visual inspection but large enough to admit water molecules over months of thermal expansion cycles. Laboratory-accelerated aging tests had failed to replicate the mechanical stress created by repeated freeze-thaw cycles in actual underground installations. The failure validated every engineering concern about material substitutions, but the timing made corporate reversal politically impossible. Dr. Harold Simpson from Bell Labs examined the failed cable with scientific instruments that revealed the systematic breakdown of every plastic component. Moisture infiltration had reached paper insulation through polymer matrix degradation that laboratory simulations had not predicted accurately. The petroleum-based treatment compounds that prevented bacterial degradation in lead-sheathed cables proved inadequate when exposed to groundwater contamination through plastic barrier failures. Simpson's materials science expertise finally recognized the difference between controlled laboratory aging and harsh real-world environments where cables would spend decades buried underground. The corporate response to catastrophic test failures demonstrated how financial pressures override engineering reality when quarterly profits take precedence over long-term infrastructure reliability. Bradford acknowledged the plastic cable failure, but argued that improved formulations would solve moisture penetration problems while maintaining cost advantages that made lead alternatives economically necessary. His presentation to corporate executives emphasized that even if plastic cables required replacement every 15 years instead of lasting 50, the initial savings would justify periodic infrastructure rebuilds. Manufacturing workers throughout Baltimore Works recognized the implications of abandoning lead cable production with clarity that escaped corporate executives focused on immediate cost reductions. Kowalski's experienced crew understood that systematic quality control procedures developed over years of refinement could not be transferred quickly to alternative materials requiring different manufacturing techniques. The controlled atmosphere extrusion chambers designed specifically for lid processing would become useless equipment when regulations banned traditional materials. Decades of accumulated manufacturing expertise would be lost permanently when the last lead cable rolled off production lines in December. The final engineering report prepared by Tulloss documented performance data that corporate executives chose to ignore rather than confront the long-term consequences of material substitutions. Controlled atmosphere lead cables manufactured at Baltimore Works showed zero failures after accelerated aging equivalent to 50 years of underground service. Voice transmission quality remained perfect, moisture penetration was undetectable, and electrical characteristics matched original specifications with precision that impressed even skeptical Bell Labs scientists. The engineering excellence that would preserve American telecommunications infrastructure for generations was being sacrificed for quarterly earnings reports that would be forgotten within months. Installation crews throughout the Mid-Atlantic region began reporting field performance differences between lead-sheathed cables and newer alternatives that validated every engineering prediction about long-term reliability. Lead cables installed in the 1930s continued providing perfect voice transmission after 15 years of underground service, while aluminum alternatives showed measurable signal degradation within 5 years. Plastic-sheathed installations exhibited intermittent connectivity problems during temperature extremes that required frequent maintenance interventions and periodic conductor replacements. The systematic documentation of superior lead cable performance created an archive of engineering data that corporate executives refused to acknowledge because it contradicted financial projections requiring material cost reductions. Tullis compiled test results, field performance reports, and accelerated aging studies into comprehensive technical documentation that proved controlled atmosphere lead extrusion-produced telecommunications infrastructure capable of generational service life. The report included prophetic warnings that abandoning proven manufacturing techniques for cheaper alternatives would force American telecommunications companies to rebuild the same infrastructure repeatedly instead of building it right once. As 1948 drew toward its regulatory deadline, Baltimore Works faced the certainty that institutional knowledge accumulated over decades would disappear when lead cable manufacturing ceased forever. The controlled atmosphere extrusion process represented American industrial achievement that transformed traditional craftsmanship into systematic engineering science, but this expertise would die with corporate decisions prioritizing immediate savings over long-term infrastructure reliability. Frank Kowalski trained his final group of workers on lead handling procedures they would never use again after December 31st, preserving knowledge that future generations might desperately need but would no longer possess. Maria Santos adjusted her digital signal analyzer on November 8, 2024, preparing for another routine fiber optic installation in Baltimore's Federal Hill District. The third-generation telecommunications technician had spent 12 years upgrading America's aging infrastructure, replacing cables that consistently failed years before their projected service life. Her diagnostic equipment represented cutting-edge technology capable of measuring signal quality, moisture content, and electrical characteristics with precision that 1940s engineers could never have imagined. The morning's work order called for removing obsolete copper cables installed in 1948 to make conduit space for modern fiber optic systems that promise 25-year service life. The first anomalous reading appeared when Santos connected her analyzer to test residual signal quality before disconnection procedures. Her instruments displayed voice transmission clarity of 99.2%, better than current digital standards and impossible for 76-year-old copper cable technology. She disconnected the analyzer and recalibrated the equipment, assuming instrument malfunction rather than accepting readings that contradicted everything her engineering training had taught about telecommunications infrastructure aging. The second test produced identical results, forcing Santos to confront data that challenged fundamental assumptions about technology, progression. Santos examined the cable marking plate with growing disbelief as she read manufacturing specifications that seemed absurdly over-engineered for telephone service. The Western Electric identification tag indicated lead sheathing thickness of 97 thousandths of an inch, paper insulation treated with petroleum-based compounds, and copper conductors meeting purity specifications exceeding modern standards. Her digital instruments detected zero moisture infiltration, no measurable corrosion, and electrical characteristics identical to laboratory-perfect conditions. The cable had spent 76 years buried underground in Baltimore's humid climate, while maintaining performance that current technology could not match after a single decade of service. The impossibility of the situation became clear when Santos compared her readings to performance data from fiber optic cables installed 9 years earlier in the same neighborhood. The advanced plastic sheath systems showed 30% failure rates, moisture contamination requiring periodic maintenance, and signal degradation that necessitated repeater installations every few thousand feet. Meanwhile, the supposedly obsolete 1948 cable delivered voice quality superior to digital compression algorithms while requiring zero maintenance interventions over 3/4 of a century. Santos documented her findings with systematic thoroughness that reflected her family's 3 generations of telecommunications experience. Her grandfather had worked telephone switchboards during the 1950s. Her father had installed cable television systems throughout the 1980s, and her own career spanned the transition from copper to fiber optic infrastructure. None of their accumulated experience prepared her for discovering that the oldest technology in the conduit performed better than everything that replaced it. The corporate response to Santos's field report demonstrated how institutional amnesia had erased memory of American manufacturing excellence within a single generation. Her supervisor, Regional Operations Manager David Chen, initially dismissed the performance data as instrument error, rather than accepting readings that contradicted corporate assumptions about technology progression. Chen's engineering background included no exposure to lead cable manufacturing techniques that had been abandoned decades before his career began. The institutional knowledge that created generational infrastructure had vanished along with the factories that perfected it. Independent laboratory testing confirmed Santos's field measurements with scientific precision that eliminated any possibility of instrument error or measurement contamination. The Western Electric cable sections submitted for analysis showed material properties that current manufacturing could not duplicate despite 75 years of supposed technological advancement. Lead sheathing maintained molecular integrity without crystalline degradation, while paper insulation remained chemically stable despite decades of underground exposure to temperature extremes and groundwater contamination. The shocking discovery that 1940s American engineering surpassed 21st century technology created cognitive dissonance throughout the telecommunications industry. AT&T engineers examined Santos's documentation with professional skepticism that gradually transformed into amazed recognition. The controlled atmosphere lead extrusion process that Tulos's team had perfected represented manufacturing excellence that modern corporations had abandoned for quarterly profit optimization. Current cable failures that required constant replacement cycles resulted directly from corporate decisions prioritizing immediate cost savings over long-term infrastructure reliability. Dr. Patricia Williams from the National Institute of Standards and Technology led the comprehensive analysis of Western Electric cable samples that revealed the systematic engineering excellence behind impossible performance characteristics. Her materials science team discovered that controlled atmosphere manufacturing had eliminated microscopic defects that caused premature failure in modern alternatives. The lead sheathing showed no evidence of galvanic corrosion, electrolytic degradation, or thermal stress fractures that plagued contemporary materials after minimal service periods. The petroleum-based paper treatment proved chemically superior to modern plastic insulation systems that had replaced it for cost reasons rather than performance improvements. Accelerated aging tests demonstrated that the 1940s treatment compounds prevented bacterial degradation, moisture absorption, and thermal breakdown through chemical mechanisms that current materials science was only beginning to understand. The treatment process had cost 4 times more than untreated paper, but field testing proved this investment eliminated replacement requirements for generational service periods. Corporate executives throughout the telecommunications industry struggled to comprehend how 1940s manufacturing techniques achieved results that 21st century technology could not duplicate. The institutional knowledge that created permanent infrastructure had been lost when companies abandoned engineering excellence for financial optimization. Modern engineers attempting to reverse engineer Western Electric's processes discovered that written specifications told only part of the story. The systematic manufacturing expertise that transformed materials into generational infrastructure had died with the craftsmen who perfected it. The ultimate vindication came when telecommunications companies calculated the true cost of abandoning lead cable manufacturing for cheaper alternatives. American taxpayers were spending $60 billion annually replacing failed infrastructure that Western Electric's 1940s engineering could have built to last 75 years. The economy of plastic materials that promised cost savings actually increased lifetime expenses by 20 times while reducing service reliability to levels that required constant maintenance interventions. The Baltimore Museum of Industry's archives yielded J. Carroll Toulous's original engineering reports that contained prophetic warnings about the consequences of sacrificing long-term reliability for short-term cost savings. His 1948 documentation included detailed predictions about failure mechanisms that would occur when manufacturers abandoned controlled atmosphere lead extrusion for cheaper alternatives. Every prediction had been validated by 7 decades of infrastructure failures that could have been prevented through systematic engineering excellence. Frank Kowalski's manufacturing procedures, preserved in Western Electric's technical documentation, revealed the systematic craftsmanship that had been dismissed as unnecessarily complex by corporate executives focused on immediate profit maximization. His detailed training protocols explained how precision manufacturing created telecommunications infrastructure capable of outlasting the companies that built it. The institutional knowledge that once made American manufacturing the world standard had been sacrificed for quarterly earnings reports that were forgotten within months. The rediscovery of Western Electric's engineering excellence created a painful recognition of how corporate short-sightedness had destroyed American manufacturing leadership through systematic abandonment of quality standards. The lead cables that performed perfectly after 76 years represented the last products of an industrial culture that built for permanence rather than planned obsolescence. Modern America was rebuilding the same infrastructure every decade instead of building it right once, paying the compounding costs of forgotten excellence.